This is the third in a series of 3 tutorials on heat transfer. In the previous tutorials, we explored how to set up a CFD model when a heat transfer rate is specified. In this particular case, we're going to look at predicting the heat transfer rate from a series of tube bundles. My name is Jeff Franklin. I'm the primary architect of Azore CFD. If you'd like to learn more about this commercial tool, please visit the website azorecfd.com. The geometry for this test case is the same as was used previously in the last 2 test cases. The difference for this particular case is how we treat these thin baffles. In the previous test cases, we treated those as perfectly insulated. In this case, we're going to assume that they are perfectly conductors so that energy will transfer from here to here or here to here through these tube bundles. Just as with the previous test case, we're going to select a number of planes that kind of intersect the model, and they're shown by these red lines, where we can use surface integrals to gather some precise information about our CFD predictions. 10 planes are selected as well as the exit plane. Much of the flow conditions remain the same as those used previously in our test cases for heat transfer. Things such as the flow rate of vapor and air remain the same, and the temperatures of those gases as they're introduced into our system remain the same. What we're interested in exploring in this particular test case is actually predicting the heat transfer rate rather than specifying it. To do that, we're going to change how the tubes are represented. For the first tube bundle, we're going to assume that the temperature of the tubes, the surface temperature, remains at 400 degrees K. Here, we'll use that temperature, the CFD tool will use that temperature to actually calculate the heat transfer rate. In the second set of tubes, we're going to assume that there's some fluid passing through those tubes with a convective heat transfer coefficient of 3000. We are going to use those two properties to actually calculate the heat flux due to these conditions. The remaining fluid properties will remain the same as what we had used previously. The first thing you want to do when you start a simulation is do some handbook calculations to get a feeling for how much energy is being added to your system. We can do that since we know the temperature and the types of species coming into our model. So in this particular case, we have water vapor coming in at a flow rate of a half a kilogram per second, and we know its temperature. And then based on that temperature, we can come up with its enthalpy value using an enthalpy curve. And the graph on the right shows an enthalpy curve for the 2 different species that are coming in here. The blue line represents our water vapor, and the red line represents our air enthalpy curves. And so you can see how the enthalpy level changes with the temperature. So in order to determine the enthalpy of our water vapor, we can look up the temperature along here, and then we can go up and find where that crosses our blue line and come over here, and we can see that a value of about this is going to be the enthalpy level of the water vapor at this temperature. The precise number is shown right here. We can do a similar calculation for our air using the red line. And so once we know the enthalpy level and the mass flow rate, we can multiply those two together, and that gives us the total energy flux for this species coming into our model. And if we add the total energy flux for both of these, we can get the total energy due to these 2 gases coming into our model, which is this value right here. Once we know the energy flux, we can use the total mass flow rate coming in here, divide that in there, and that allows us to find a mixture-weighted enthalpy. And once we know the mixture-weighted enthalpy, we can look up a value for temperature that would represent that mixing process. So if we look over here, we're looking at a mixture enthalpy of about this value, which is right in this area. And then we would follow over here and see where that intersects our green line, because our green line represents 50% air and 50% water vapor, which is what we have. And then we move down here and we can see that we kind of expect a temperature of that mixture to be somewhere between 800 and 900, and that number comes out to be precisely this number down here. So now we know what the mixture temperature of our gases will be in our model. So in the previous test cases that we looked at, we knew the amount of energy that was being removed by the tubes. In this particular test case, we are actually predicting that. And so that's what we have. So we know from our previous slide what the total inlet flux going into our model, we have that value right here. And from our model, once it's done, we can query it and ask for the first set of two bundles what the total heat flux would be on the surface of that first tube bundle. What does the CFD model say it would be? And once we know that in the tube area, we can actually calculate what the total energy addition would be. And in this particular case, since the tubes were cooler than the gas stream, it removed energy from our system. So then in the second set of two bundles, we also got a predicted heat flux rate right here, and we multiplied it. It happens to be the same amount of tube area. And in this particular case, it's a positive value, so we added energy in. So now we've used our CFD model to look and predict those heat flux rates. And once we know those heat flux rates, we can do a little bit of a handbook calculation to determine what the outlet temperature should be based on this amount of energy removal and addition. And so we have an outlet heat flux of this value. The mass flow rate remains the same as 1. So now we know the enthalpy level coming out. And so we can go over here and look and see where it would be. If we go over to our green line, we can see that we hit our green line right about here. And then we go down right about here. And so we're kind of expecting in this model to have an outlet temperature due to energy balance to be 840.56 to be very precise. That should be what our model should predict, and any surface integrals, that's what it should report to have an energy balance value. So we've selected a number of planes that we want to use to extract average values in our model. But there are different methods that you can use in order to determine an average value. And in particular, we're going to be focusing on how would we determine an average temperature value? And I've kind of outlined 3 different ways to come up with an average temperature on a particular surface in our model. And the first method that we're going to look at here is, I'm calling it an enthalpy balance one. This is an energy conservative method for coming up with an average temperature on a surface. And that basically begins by looking at the heat flux through. So this is the enthalpy times the density times the velocity times the area. So this is the enthalpy of the mass piercing the surface. So every surface that is composed on our surface integral. So that kind of characterizes the convective portion of the energy crossing the boundary of our surface. But there's actually one other mode of heat transfer that we're going to try to account for in this energy integration, and that is the fact that you can always have a temperature gradient across your surface, which implies a certain amount of energy flux due to conduction through the surface. And that's what this term right here represents, where we have the temperature gradient normal to the surface times K, which is the effective thermal conductivity, times the surface area. And that gives us your total energy flux through that surface, and then we divide it by the mass flow through that surface, and that gives us an average enthalpy value. So this is kind of very similar to the handbook calculations we've done in the past. And then once we know that average enthalpy value, we can use those enthalpy curves to actually calculate an average temperature. And this average temperature will be one that you would expect that represents what you might expect from a mixture average standpoint. Another method that you might want to use to determine an average temperature value would be a mass flow weighted value. In this method, we take the density times the velocity normal to the surface times the area, And that's the mass flow rate, and then we multiply it by the temperature, and we sum all of those up, and then we divide by the total mass flow rate, and that gives us yet another representation of the average temperature. The last method is an area-weighted method. In this method, we simply multiply the temperature on each facet by the area of that facet, sum it all together, and then divide by the area, and that gives us yet another representation of the average temperature, and that would be an area-weighted average. And so for this model, we have a bunch of different planes, and we're going to look at how the predictions of these surface integrals differ depending on the surface integration method you choose. So now we're going to look at the temperature distribution through our model. And in particular, we're going to look at the surface integrals that we're going to get due to the temperature distributions that we see here. And so what I've done is right over here on the right, or the left, you can see the temperature distribution that was predicted for this particular model. And on the right is a graph that shows the temperature at each one of these planes due to the surface integral. And there's a surface, each one of the different surface integration methods. The red line represents the enthalpy-based or the energy conservative-based integration technique. The blue line represents the mass-weighted temperature, and the green line represents the area-weighted temperature. And one thing you might notice here, so like say for instance, this is the very first point, which is plane 1. So that would be this plane right here. And one thing to notice here is there's a large disparity in what the average temperature is based on these different methods. You'll notice that the enthalpy-based one is very close to the value we would expect from our energy balance calculations, and these other two are quite a ways away from it. And one might say, well, that's not a very good integration method, but that really depends on what you're trying to evaluate. For instance, if you, for instance, had right here along plane 1, you had a bunch of thermocouple rakes, and you got an average temperature from those thermocouple rakes that was based on an area-weighted average, then you would want to use this green line and this value from the green line to determine the average value. So it really depends on how you are digesting the data that you're gathering from the model. Likewise, if the test data that you collected here was temperature and velocity, and the average value was using the velocity and the temperature so that you could come up with a mass-weighted value, you would use this value here, which is the mass-weighted average. So there's different reasons to use different averaging methods, but if you are interested in energy conservative values, it's important to use the enthalpy-based method so that those don't defy what your expectations are from an energy balance standpoint. For completeness, I've provided this table over on the right that shows the actual values. One thing to note here is that the energy balance method, which is this first column right here, we predicted that the temperature at the outlet should be this number right here. So right after the tube bank, right here at P7, we're at the temperature of 840, which is kind of what we thought it should be, and it remains that temperature. The other ones kind of depart from that, but as the mixture becomes more uniformly mixed, it progresses toward the value of 840 degrees. And so and that's what you would expect, and that's what your CFD tool is doing, is it has the actual value, it's just how you integrate it. So in summary, we've reviewed a mixing chamber and the geometry. This is, of course, the third case that we've looked at for this particular geometry. We've reviewed how the tube bank energy exchange happens and how we changed it. We've again reviewed surface integration methods, and then we've looked at the energy balance in these curves to look at how the temperature changes as the energy is removed and added into our system. As always, if you're interested in more information about tutorials such as this one, please visit the website azorcfd.com, or you can look at our YouTube channel, Azore CFD, to find more technical content like this.